Hi, I am Lopamudra Sen. Welcome back to my channel Electronic Science Tutorial. From today I will start a new lecture series on NTA UGC NET and West Bengal SET exam for Electronic Science subject. Those who are not check out my channel, please follow my channel. If you like my channel, then please do like, share and subscribe my channel. So let's start our class. In today's class, we discuss about the NTA UGC NET and West Bengal SET exam 2022. In this session, we cover in detail about this topic so that we can easily solve the previous year question paper of UGC NET Electronic Science. Each and every topic we can understand in easy and simple manner. So, let's begin our NTA UGC NET exam 2022 class. Okay. Today I will discuss one of the most common important topic of semiconductor device, that is the electron concentration in the conduction band. Okay. Say this is conduction band which is represented by EC energy, and this is valence band which is represented by EV energy, and the Fermi level lies between the conduction band and the valence band, and this is represented by EF. Okay, we know that the valence band is full of electron band and the conduction band is empty band or partly filled band, right? When we externally excited these valence electrons reach from valence band to the conduction band and current flow will start, right? So EF is the highest occupied energy state, which is known as the Fermi energy. Now we concentrate in the electron concentration in the conduction band, in which term electron concentration depends in the conduction band, that is what is quantum state? Discrete energy state is called quantum state, right? So allowed discrete quantum state between the conduction band is one term for electron concentration in the conduction band, which is the main term of the electron concentration in the conduction band. Number of allowed quantum state, that is the density of states, number 1 point, and the number 2 point is Fe, which is the Fermi-Dirac probability function. So we can say that the electron distribution in the conduction band depends on in two terms. One is the discrete density of state or quantum state, allowed quantum state, that is GCE, where GCE is represented the density of quantum state in the conduction band, and the another important topic, that is Fe, which is called the Fermi-Dirac probability function. So these two topics or these two terms are important for electron concentration in the conduction band, right? Okay. So what is the total electron concentration per unit volume in the conduction band? That is if we integrate the density of allowed energy state and Fermi-Dirac probability function within the conduction band range, then we get the entire conduction band energy. So in this way we can represent this equation, that is N0 is the electron concentration in the conduction band, and which we will get by integrating the density of allowed energy state and the Fermi-Dirac probability function. So this is the next step to getting the electron concentration in the conduction band energy. Okay. Next, then we consider for electron concentration in the conduction band, we have E is the greater energy than conduction band energy, right? So this is the condition when E is greater than EC. If E is greater than EC, that means if EC minus EF, EC is the conduction band energy. Just a minute, we know this is the conduction band, this is the valence band, and this is the Fermi energy. So this is EC, this is EF, and this is EV, right? For electrons in the conduction band, what we get? We get that is E is greater than EC. That means this energy. EC means conduction band energy. If EC minus EF, EC is higher than EF. So EC minus EF greater than KT. KT is the Boltzmann constant at absolute temperature. Then we can say that E minus EF also greater than KT. That is K is the Boltzmann constant and T is the absolute temperature. Okay. So this is the Fermi-Dirac. From this point we can get the Fermi-Dirac probability function reduces to Boltzmann approximation. And so here we consider this condition. So the now we can, what we get, now we reduce the Fermi probability function to Boltzmann approximation. Okay. So we know Fermi energy equal to 1 divided by 1 plus exponential E minus EF by KT, which is nearly equal to, if we reciprocate this function, what we get, that is exponential minus E minus EF divided by KT. So this is the equation number 3, and this is the reduces form of Fermi probability function to Boltzmann approximation. Okay. Now we applying the Boltzmann approximation with the thermal equilibrium density of electrons in the conduction band, that is N0 equal to limit, integration limit. Why this is infinity and this is EC? Because we consider EC energy, that means conduction band energy. So the lower limit is EC, right? The integration lower limit is EC, and the upper limit of integration should be the top of the allowed conduction band energy. Here we consider discrete energy state, the discrete allowed energy state. So the top of the allowed conduction band energy is the upper limit of the integration. Since the Fermi probability function rapidly approaches to 0 with increasing energy, we can take the upper limit as infinity. So here we write the upper limit is infinity and the lower limit is EC energy. And in previous class we already talked about this topic, that what is the value of GC, GCE. The value is 4 pi, that is GCE is the density of states in the conduction band. So the value is 4 pi 2 mn star divided by h cube 3 by 2 power root over E minus EC, and this is the reduces form of Fermi probability function. So this is, here we write exponential minus E minus EF divided by KT dE. This is the equation number 4. Okay. Let us consider eta equal to E minus EC divided by KT. So we can write this equation number 4 becomes N0 equal to 4 pi 2 KT mn star by h cube 3 by 2 power exponential minus E minus EF divided by KT. This is the constant part, and we can here we write this term. Okay, and in the integration part here we can write that is the upper limit is infinity and the lower limit is 0. Here we can write this, right? So here we write that is eta to the power half exponential, that is for this value eta we can write that eta is eta to the power half and exponential minus eta d eta, which is represented by equation 5. Okay. So what is the integral function part? That is integration limit 0 to infinity eta to the power half exponential minus eta d eta, that is equal to half root pi, and this value is this value is for gamma function of the integral part. So this is we from this integral part we get that is half root over pi. Okay, so this is the equation 6. So from equation 5 what we get, that is N0 equal to 2 into 2 pi kt mn star divided by h square power 3 by 2 exponential minus EC minus EF divided by KT. Okay, we can define this term by NC, that is the 2 pi kt mn star divided by h square power 3 by 2. This part we can represent it by NC, and this NC is the effective density of state function in the conduction band. So the electron concentration in the conduction band is N0 equal to NC exponential EC minus EF divided by KT. This is the final part or the final equation of the electron concentration in the conduction band. That is N0 equal to NC exponential EC minus EF divided by KT. Why we write here EC minus EF? We already talked about this topic because conduction band energy is higher than the Fermi energy. So here we write EC minus EF. Okay. So this is the final term or final part of the electron concentration in the conduction band, that is N0 equal to NC exponential EC minus EF divided by KT. I hope you understand. Thank you. Here we end today's session. Thank you. I hope you love this informative session of NTA UGC NET or West Bengal SET exam. If you like my video then please do like, share and subscribe my channel. फिर मिलते हैं एक नई वीडियो के साथ. Thank you.